Good evening, ladies and gentlemen. Before I kick off, I'd like to thank the organizers of the Langley Lectures for inviting Ian and myself back to talk to you again about the experiment that mankind is carrying out on the planet. In the 12 months since we last stood, or in my case sat, before you, a lot has happened. 2016 became the new warmest year on record, easily beating 2014 and 2015, each of which had been in turn the previous warmest years. We now live in a world that is more than 1 degree Celsius warmer than it was in pre-industrial times. The cartoon in front of you shows the likely results of warming the climate even further. Some of the predictions won't happen immediately. For instance, sea level rise takes some time to respond to warming. So that by 3 degrees Celsius of warming, expected later this century, New York won't immediately be inundated. Although in the meantime, it will be at increasing danger from storm surges. And in the same way that sea level rise takes time to get going, it also takes a long time to stop. There will be no quick fix for this one. All of this begs the question of exactly what is going to happen, and over what time frame. As ever, it all depends on the point at which humanity wakes up to the danger. No doubt you all got the relevance of the ostrich slide. Let me take you back a little over 12 months to the Paris Climate Accord. In the run-up to the meeting, all of the nearly 200 nations that attended, made emission reduction pledges. Of course, all of the emission reduction promises are welcome. Unfortunately, they were grossly inadequate. Even after the reductions are taken into account, we are still looking at between 3 degrees Celsius and 4 degrees Celsius of warming by the end of the century. And this was the meeting that agreed to try to keep warming to no more than 1.5 degrees Celsius. I'd like to give you an example of what warming on this scale really means. I have a question for you. At the height of the last glaciation some 21,000 years ago, ice sheets 2 miles thick extended across North America and Eurasia. Yet, 13,000 years later, cyclical changes in the Earth's orbit had warmed things up sufficiently to give the climate that allowed human civilization to develop. My question is, as a global average, how many degrees C warmer did the planet become to melt all that ice and give us the world we are familiar with? So, here is a picture of Teg's nose some 21,000 years ago, complete with a few locals inspecting the ice sheet. And here is an image of Three Shires Head complete with a modern climate. So, how much warmer is the planet on the right, compared to the planet on the left? The answer is 5 degrees Celsius. It doesn't seem enough, but bear in mind that this is the amount of warming averaged over the planet. As indeed is the 1 degree Celsius of warming that mankind is already responsible for. Now, if a warming of 5 degrees Celsius turns the picture on the left into the one on the right, hopefully you can see why we should be very concerned about what is happening to our planet. So, the thesis I want to explore for the next 15 minutes or so is that of course the climate has changed before. In fact, it's changed quite frequently. So frequently that the geological record is packed full of evidence of what's likely to happen. Unfortunately, the evidence paints a starkly pessimistic picture of what we can expect unless we wake up very quickly. I am going to talk about 2 examples of past climate change. The first is the end of the most recent glaciation. At this time, in the northern hemisphere, glaciers retreated from the latitude of the Thames, all the way back up to the Arctic. Sea level rose by 120 meters in response to the melting, causing immense change over the whole planet. I also want to talk a little bit about a climate change event that was more similar to the current situation, in that it was caused by a buildup of carbon in the atmosphere. This event happened around 56 million years ago and is known as the Paleocene to Eocene thermal maximum, commonly abbreviated to PETM. The graph shows the rate of warming during the PETM in blue, compared to what is happening today in red. As you can see, today, we are warming the planet perhaps 100 times more quickly than during the PETM. Even so, the PETM provides some important lessons about what we are doing to our oceans. For each of these two events we will consider both what happened, but also the impact the event would have had if a 21st century human civilization had been present on the Earth at the same time. The image shown here is a representation of central London with a projected sea level rise of 5 to 8 meters. As we'll see, we are already committed to sea level rise of this magnitude. It'll just take the planet a while to catch up. I need to very quickly take you through the events at the end of the most recent glacial period. The Earth has actually been in an ice age for the last 2.6 million years, a period geologists call the Pleistocene. During the Pleistocene, there were many advances and retreats of the ice sheets, although there has always been ice on both Greenland and the Antarctic. This is the definition of an ice age. It is reasonably well understood that the ebb and flow of ice sheets has been controlled by orbital cycles, with significant help from powerful climate feedbacks. The last glacial maximum was around 21,000 years ago, after which the climate began to warm and the glaciers began to melt. The experts say that the planet entered the current interglacial around 12,000 years ago, although things didn't really stabilize before about 8,000 years ago. By the time we had reached stability, the ice sheets had melted back to the poles, and sea level had risen 120 meters. I need to emphasize that the 8,000 years since sea level stabilized is the period within which human civilization developed. The stability of the climate over the last 8,000 years is shown very clearly on the next diagram. This diagram shows a reconstruction of sea level over the last 24,000 years. The bottom axis is time. Today is on the right, whilst 24,000 years ago, just before the glacial maximum, is on the left. The glacial maximum itself is marked on the diagram on the left-hand side at the bottom. The scale on the vertical axis is in meters. The curve shows how sea level changed over this period as the glaciers melted and we moved into the recent stable climate. As you can see, sea level didn't rise steadily. Starting soon after the glacial maximum, there is a slowly but accelerating rise in sea level. Then around 14,000 years ago, things really began speeding up with several periods of very rapid sea level rise. By about 8,000 years ago things began to stabilize as the ice sheets became established in the positions they've had for the last few thousand years. I want to draw your attention to the phase of rapid sea level rise labeled Meltwater Pulse 1a. This happened after the much slower rise in sea level that had been occurring since the last glacial maximum. This is interpreted as the start of the wholesale collapse of the ice sheets. During Meltwater Pulse 1a, sea level rose at a rate of between 3 centimeters and 6 centimeters per year for a period of 400 to 500 years. 6 centimeters doesn't sound too much, but do that for 10 years and you have 60 centimeters. Do it for 50 years and you have 3 meters. It is estimated that the ice currently sitting on top of Greenland and the Antarctic represents perhaps 80 meters of additional sea level rise. The best indication we have of what might happen next is in front of you. It's likely that we are currently in the equivalent of the slow sea level rise experienced in the long period following the last glacial maximum, running up to the start of Meltwater Pulse 1a. Perhaps we have some time to think about what might happen next. Except the climate change that we are driving is happening much more quickly. A quick quiz. How many people, across the world, live within 1 meter or just over 3 feet of sea level? The answer is perhaps 150 million people. Once sea level has risen by half a meter or so, a very large number of people will need to find somewhere else to live. There is very little doubt this will happen within the next 80 years. Another question. The interglacial before the current one, known as the Eemian, was perhaps 1 degree Celsius warmer at its peak than was the current interglacial. How much higher do you think sea level was during the Eemian for that 1 degree C of extra warmth? The answer is between 6 meters and 9 meters. Given we have already warmed the planet by more than 1 degree Celsius, it is likely that sea level rise of this magnitude is already locked into the system. It'll just take some time for the planet to catch up with us. Here again is that picture I showed of London under about that much water. The question therefore isn't whether this will happen, but when. We probably have a few centuries before reality begins to bite, but an awful lot of humanity, including many in this country, don't have that small comfort. Okay, let's look at something similar in many ways, to what's happening today. Although the PETM occurred a long time ago, it gives an excellent example of what happens when you put immense amounts of carbon into the atmosphere. So, the PETM forms the boundary between two geological eras. In fact, many of the geological eras that you might be familiar with, the Devonian, the Permian, the Carboniferous etc., were originally named because of very obvious differences in the fossils found within each unit. We now know that in many cases the end of a geological era coincides with a period of planetary climate change that drove many species extinct. As I keep saying, climate change has happened before, and it is never innocuous. Even before the PETM warming, the Paleocene climate was quite a bit warmer than it is today. There was no permanent ice at the poles, a situation known as a hothouse Earth. Consequently, the PETM warming produced no significant sea level rise. As we'll see, it did however produce other changes to the Earth's oceans. The most likely cause of the PETM was a release of methane from the ocean floor. As marine organisms die, they sink to the seabed and decompose. If there is limited oxygen, then the result of organic decomposition is the production of methane. If the seabed is deep and cold enough, the methane becomes frozen and can build up immense quantities over millions of years. Some of you will be aware that the same situation is true today. The PETM also coincides with volcanism associated with the opening of the North Atlantic. It has been suggested that this volcanic warmth might have thawed the methane sufficiently for it to bubble to the surface over perhaps 10 or 20,000 years. Whatever the trigger, it seems that a very large volume of methane with a biological origin was released into the atmosphere. Methane is a very strong greenhouse gas, although its residence time in the atmosphere is much shorter than carbon dioxide. Unfortunately, much of the methane in the atmosphere will have ultimately degraded into carbon dioxide anyway. We have no reliable thermometer to tell us how much warming occurred during the PETM. We do however have proxies which imply warming of somewhere between 5 degrees Celsius to 8 degrees C. The warmth lasted approximately 200,000 years. This is in line with the rate of removal of carbon dioxide from the atmosphere. Some of you might be familiar with the Gaia hypothesis of James Lovelock. In some ways the hypothesis is correct. The planet is able to moderate its own climate by the removal of carbon dioxide via the weathering of rocks. A process that speeds up when the climate is warm, and slows down when the climate is cold. Unfortunately for us, even in a warm climate, it takes the Earth around 100,000 years before significant change is achieved. The climate change that occurred during the PETM caused immense changes to the plants and animals that lived on the land. It also caused changes in the oceans. I need to spend a few minutes explaining what you are looking at, and the easiest way is to think about something a little more familiar. The rocks we see around us, for instance these, which you may recognize from the top of Teg's nose, provide evidence for what was happening at specific times in the history of the planet. Some of you may know, these rocks were laid down by a large and meandering river perhaps 315 million years ago. The whole sequence may have taken hundreds of thousands of years to be deposited. As you can see, today, this quarry forms the top of the formations at Teg's nose. Hence we have no information on what happened next. It seems that after these rocks were laid down, the area was no longer undergoing active sedimentation. Perhaps because the area was above water level. If we want to know what happened next, we will need to look elsewhere. Hence, most of the geology we see around us is a snapshot of what was happening in specific places over a limited time. This is a bit of a pain, because the best evidence for changing environments would be if we had a large thickness of rock that was laid down constantly, without gaps, over very large periods of time. Fortunately, such a place does exist. The ocean floor. Some of you will be aware that compared to the age of the Earth, the ocean floor is actually quite young. This is because it is created and then destroyed by plate tectonics. However, there are places on the planet where the ocean floor is more than 150 million years old. Consequently, if we drill deep cores in these sections of ocean floor, we are able to sample continuous records of sedimentation going back for reasonably long periods, and running up to pretty much the present day. Here indeed, is a short section of ocean sediment. You are looking at sections of drill core taken from the North Atlantic. The actual core is hundreds of meters long, but for ease of storage it is chopped into short sections. This then is a small section of the complete core. The cores you see in front of you correctly stack on top of each other. The youngest part is on the left, the oldest on the right. The blue tape marks the top of each section. Is that reasonably clear? The section of core we are looking at is the very top of the Paleocene and the lowest part of the Eocene. Can anyone guess where the Paleocene stops and the Eocene starts? The red band is indeed the boundary, and it marks the period of time over which the PETM was driving climate change. Given the known sedimentation rate, it is estimated that the red band represents a period of approximately 200,000 years. If we look away from the red band, the rest of the core is quite lightly colored. This is because it contains the calcium carbonate skeletons of ocean-living microorganisms. These lived much higher up in the ocean, but once they died their remains accumulated on the seafloor. The red band is essentially composed of iron-rich sediment. In fact, the same sediment also exists in the white sections of core, it's just that there is so much carbonate that the red coloration is lost. So, the difference between the PETM red band and the rest of the core is that for a period of around 200,000 years there was significantly less carbonate-based life living in the oceans. Can anyone suggest why this might be? The answer, of course, is an increase in ocean acidity due to the vast amounts of carbon dioxide which dissolved into the oceans during the PETM. The additional acidity promotes the dissolution of calcium carbonate, making it far more difficult for carbonate-based life forms to thrive. In addition to microscopic life, carbonate-based life in the oceans also includes shellfish and corals. If we jump to today, it is estimated that about 25% of the carbon dioxide emitted annually by mankind ends up dissolved in the oceans. The acidity in today's oceans has increased by 40% compared to pre-industrial times. This is already impacting commercial shellfish beds because in some areas, oysters and other shellfish are struggling to make sufficiently strong shells. 2016 saw the most extensive coral bleaching ever observed. Whilst this was driven predominantly by high ocean temperatures, the extra work corals must do to keep their structures intact in an increasingly acidic ocean environment also has an impact. Okay, my conclusions. This quote is from an American politician and highlights the responsibility that everyone in this room has to the future. What has been started cannot now be stopped, however, all of us are responsible for the severity of what follows. These thoughts are my own. I am now going to hand over to Ian, who has examples of what we can all do to change the future. All we need to do is heed the message.